Hello and welcome to our lower limb exoskeleton project demonstration. This is the overall block diagram in which we use to reference throughout the entirety of our project. The main points to highlight here will be the separation of the peripheral electronics from the motors and their control boards, as well as the methods of logic and control for keeping the user safe and assisting the user as intended. First of all, you will notice two separate batteries. The 9-volt powering the Arduino and sensors, and then the 20-volt 2 amp-hour batteries for the motors and control boards. We realized early on that we would need to separate the two as there was no reliable way of stepping down the 20-volt battery for the Arduino control board and accelerometer sensors. However, all the components do interface with each other on the software side for a complete and working logic system. The sensors take data from the user, sensing when a step is being initiated. The Arduino processes this data and sends it on to our DC motor control boards, which in turn regulate the power from our 20-volt batteries and engage the motors. Finally, the Arduino is looking for data from the sensors that the user is finishing their step and tells the control board to disengage the motors. Here is a more detailed look at the power system. Here we can clearly see the three phases of our system. In phase 1, the 9-volt battery powers the Arduino through the voltage regulator, which in turn will power the 4 accelerometers. We have 2 sensors per knee joint. In each leg, there's one on the top half where the hamstring is, and then one on the bottom half where the calf is. Moving on to phase 2 and 3, these are identical, and there's one per each leg. You have the left and right. Each motor and control board is powered on its own by a 20-volt 2 amp-hour battery. The control board regulates the power sent to the motor and is actively processing information from the Arduino and sensors. The key spec for our system is the electronic system response to ensure user compatibility. This is at utmost importance as the device must react to the user as they need its assistance. A few requirements of the system is for the sensors to react as the angle of the knee changes, for the motors to respond to the control system quickly and efficiently, and for the system as a whole to react and engage a user in a step within 5 milliseconds. This video will showcase the location of all electronic and mechanical components of our lower limb exoskeleton. Thanks to our adjustable hip and knee joint attachments to the body, this device can be easily worn by anyone. Once suited up, the first thing the user will do is plug in the 2 DeWalt batteries with holsters found at either side of the waist. Then, found on the back, is the brains of the operation, the Arduino control board, the 9-volt battery, and its regulator, as well as all the wiring for the logic system. Moving down, we have a hip joint at each side, allowing 3 degrees of freedom, then the knee brace, which is secured to the user. Finally, found at each knee joint are 2 accelerometer sensors and a motor with a pulley system attached. As you can see, all wires are managed and out of the way for the user's freedom of movement. Moving on, here is a demonstration of our system. In this video, you can see how the user will experience a full range of motion familiar to what they would expect without any aid or device. Thanks to our ergonomic design, any user can enjoy and benefit from our lower limb exoskeleton system. The out-of-the-way and easy-to-use battery holsters allow for quick, on-the-job battery swaps with batteries commonly found in a work environment. And conveniently placed on the back is an on and off switch. The easily adjustable knee joints allow for users of all sizes to use this device. The user can squat low to pick up equipment from the floor and can use each leg as they would normally. As you can see, all wires, motors, and electronic components are neatly arranged and do not hinder the user in any way. Here we demonstrate how the device... Alright, start now. Here we demonstrate how the device is expected to be used in the field. Thanks to our design allowing us to interface with all the equipment that the linemen already use, the movements will already be familiar to them and allow for rapid deployments in the field. Here we see the user mounting the pole using the gaff system and harness given to us by FPL. As you can see, it is seamlessly interfaced with our lower limb exoskeleton, allowing for a rapid ascent up the pole. The user is effortlessly climbing the pole thanks to the assistance provided by the exoskeleton we designed. He is using the exact technique and equipment that FPL linemen already use. With each step, our exoskeleton relieves 10 to 15% of the load from the worker, which can really add up over the duration of a climb and throughout the workday. Now we will demonstrate a system failure. We turn the device off using the power button on the back while our climber is still on the pole. In this event, the device will be completely powerless and not pose any additional threats to the user, giving them their complete and unassisted freedom of movement. In this situation, our user will climb down the pole without the assistance of the device, proving that our exoskeleton can only assist and does not hinder the worker in any way. Specification number 1, being the most important, is our safety system. In other words, our fall detection system. We have embedded code in each of the accelerometer sensors to use the total acceleration of the device to detect a near free fall. When this is achieved, the whole system is put into an emergency shutoff to prevent the user from experiencing any further injury. In this demonstration, the sensors detect an 8-foot fall once the device is dropped and shuts down the device until it is reset. In our experimentation of the safety system, we ran 3 separate experiments with 10 trials each. Considering our specification to have a max reaction time of 500 milliseconds, the system obviously exceeds requirements with an overall average of 156 milliseconds. Specification number 2 is the knee torque produced by the motors. The minimum torque required by FPL is 10 Newton meters. Unfortunately, our motors are only capable of producing 8 Newton meters each, at the most. However, by utilizing a 1-to-4 gear ratio, we were able to exceed this requirement. First, we weigh the weight and the device to give the true weight of each experiment. For the 2.5 pound and 5 pound weights, we get 3.8 and 6.2 pounds respectively. In this benchtop demonstration, we are producing 16 Newton meters of torque at 325 RPMs with no loads in the motor. When testing with 2.5 pound load, we have 24 Newton meters at 650 RPM. Finally, with a 5 pound load, there are still 24 Newton meters, but at 800 RPM. Here are the results of the experiment using the formula for torque found in the top right of the slide. We conclude that our motors are capable of producing more than the required 10 Newton meters. Spec 3 is the reaction time of the device. The device is required to react to the user's needs within 750 milliseconds. To achieve this, the sensors must respond accurately to angle changes in the knee. Then the sensors need to send this information to the Arduino for it to process and send commands to the motor control boards. All of this must be done in a timely manner. In this video, the user is demonstrating the device's reaction time by climbing and descending a flight of stairs. The user is ascending the stairs as he would normally and looks very natural. The design and movements are very human. In his descent, he is assisted and looks very agile, while he swiftly but carefully takes his steps down the stairs. As you can see by the timer in the lower right-hand corner of this video, we are achieving our required spec of less than 750 milliseconds of reaction time per step. Using the data collected from the electronic system reaction, we ran an overall average of 0.658 seconds, or 658 milliseconds, for this device to react to the user's step.